There are some complications and miscellaneous issues that arise from the use of logical effort to optimize logic chains. First of all, when we had the expression of TP and we wanted to optimize it, so this is TP for a chain of random logic, so we have to use Pj plus Gj times Fj over gamma. And then we proceeded to differentiate this expression of Tp and equate the derivative with null to find the minimum value of delay. So when we did this, we expanded so that we had Fj equals Cgj plus 1 over Cgj, and we said that we only have two terms where Cgj makes an appearance. This doesn't take into consideration one fact, that Gj is also a product of, is also a ratio of gate capacitances. So this is a very important question. Specifically, when you did the differentiation, you took into consideration the fact that Fj was Cgj plus 1 divided by Cgj, but you did not take into consideration the fact that Gj was also a ratio of gate capacitance, specifically Cgj divided by Cgate of the inverter. So how come you didn't take into consideration this fact that the logical effort was a function of gate capacitance? In fact, it is necessary to never take into consideration this. You have to ignore the appearance of Cgate in Gj, because if you take Cgate as a variable within Gj, it will give you the wrong solution. And the reason is G, electrical effort, is a constant with respect to size. So it has nothing to do with size, right? So you cannot assume that it is a function of gate capacitance, because gate capacitance is directly related to size. And yet, a logical effort is not a function of size. So how do you square these two circles together? Like, how come you calculated a logical effort as a ratio of gate capacitances with Cg making a clear appearance, and yet at the same time G should be a constant when you differentiate with respect to Cgj? Like, how does that make sense? Because when we look at G, it is true that G can be calculated as the ratio of gate capacitance when we have actually done the final sizing, but the general definition of G is that it is the ratio of R gate times C gate by R inverters times C gate inverter. So this product, R times C, is going to be constant, and it's going to be independent from the size of the gate. And so G is going to be a constant, and it's going to be independent of the size of the gate. In fact, we explicitly discussed why G can be calculated for any gate size, and therefore we shouldn't write Cgj in this case. More accurately, this should have been something else. It should have been C gate of the gate. So Cg gate, it is the C of the gate, which is the C of the gate for any random size. In this case, when we calculate G as the ratio of just Cg gate by Cg inverter, this is specifically the input capacitance of the gate when we have sized it for resistance equal to the unit inverter. And so G is a constant. It should not be differentiated, and we should only differentiate the appearances of Cg which appear from fan-out. So the derivation we did was completely correct. So this is one complication we had to deal with. The other question we have to ask is, if we look at the sequence of operations we did to optimize a logic chain, what we did was that we first calculated F capital as CL by Cg naught. Then we calculated G capital as the product of all the small g's, because we can calculate the g's as soon as we see what the logic chain is made up of. And then we can calculate H capital, which is the product of F capital times G capital. And then we can calculate H optimal as the nth root of H capital, which is the nth root of F times G. Once we calculate H optimal, it's equal to F times G for any stage J. Because we know the G's, the logical efforts of all the stages, we can find out Fj for any stage as H optimal divided by Gj. Once we know F optimal for any stage, we can know its size, because we know the size of the first gate, which allows us to find the size of the second gate from f optimal, and we can proceed down the chain, sizing all the gates in the chain. So what's interesting about this solution is not what makes an appearance in it. What's interesting is what's absent from it. And what's absent from the solution is P. We don't see Pj making any appearance here. So the intrinsic delays or parasitic delays of stages do not make an appearance in the optimization problem. We can solve using just fan-outs, logical efforts, and total efforts. So does that mean that intrinsic delay is not important? We do not need to calculate the values of Pj's? No, of course not, because if you look at the expression of Tpj for any stage, it's equal to Tp naught into Pj plus Gj Fj over gamma. Now, once we have finished optimization, we actually find that the product Gj times Fj is equal to a constant called H optimal. So Tp optimal, the total delay for all the stages when they are summed up, is going to be equal to n Tp naught times H optimal over gamma, plus some term which is going to be equal to the summation of Tp naught Pj. So this term actually represents the summation of all parasitic delays in all the stages. So yes, P's make a huge difference because they affect the value of optimal delay that we can obtain. However, they do not make an appearance in optimization, meaning that they do not affect the optimal sizing that we have to use. So even though they do affect the value of the optimal delay, they do not inform our choice of optimal sizing. And that makes sense because parasitic delay is just going to be there. It's going to be there whether the gate is large or small. And it's also contained within the gate itself. It is not affected by the previous gate, is not affected by the next gate. It has nothing to do with what's happening in the chain. And so it's a constant. If you do any kind of differentiation, it's going to disappear. But when you go back and calculate total delay, it's going to make an appearance again. At this point, it's important to notice that there is an alternative terminology that is sometimes used when dealing with gate delays. So sometimes gate delay is expressed as Tp naught into Pj plus Gj times Hj over gamma. And in this terminology, H is actually used in place of fan out, Fj, and is given the name electrical effort. So I'm just using Fj as a term that we used with inverter chains. I keep using it with logic chains because it really still has the same meaning. But sometimes H is used as an indicator of F instead of an indicator of the total effort G times F. There's one more thing we have to talk about insofar as logical effort is concerned, which is the logical effort of gates that do not have simple inputs. And a very typical gate to consider in this case would be like an XOR gate or an XNOR gate. Because XOR and XNOR are kind of annoying because if you look at them, they have A and B, and they also have A bar and B bar. So they have an appearance of both A and A bar and B bar. Now we know that A and A bar and B bar are not independent from each other, meaning that when the input A is activated, this means that the input A bar is also activated and vice versa. So when you actually want to calculate the logical effort of input A, do you calculate the logical effort of input A alone or of input A and A bar or what? So here we describe three different types of logical effort. First of all, we describe the simple logical effort, which is the logical effort we have talked about throughout this module. So for simple logical effort, we are talking about only one input, A, B, or A bar, or whatever. So GA and GA bar and GB and GB bar for this gate are all going to be 4 plus 2, which is the input capacitance we see from one of the inputs, divided by 3. So it's going to be 4 plus 2 divided by 3, which is 6 divided by 3, which is 2. But now the question is, do you actually ever, in such a gate, activate the capacitance of input A alone? Because that never happens really, because what happens is input A bar comes through an inverter from input A. Now this complicates matters a lot, and so we introduced two concepts that help us deal with this. First of all, something called G total, total logical effort. Total logical effort assumes that all the inputs of the gate are activated. Everything is shorted and everything is activated at once, meaning that we switch the entire input capacitance of the gate at once. And so in this case, we are going to switch everything we see at once, A and A bar, B and B bar. And so we're going to have 4 times 4 plus 2 times 4 capacitance switched divided by 3. So that's going to be 16 plus 8, which is going to be 24 divided by 3, which gives us a value of 8. This is not a very useful value for logical effort, because when you switch a gate, when you switch every input for the gate, it does not produce a meaningful logical output. So this is just an indicator. It is not a useful measure to use. What is useful is to use something in the middle between what we call simple logical effort and total logical effort. And this is called group logical effort or bunch logical effort. And in this case, we're going to assume that A and some related inputs are also activated at the same time. So A and something related to A is activated at the same time. So this is going to calculate the input capacitance switched when A and A bar are both active at the same time. And so we're going to have 2 plus 2. These are the input capacitances seen from A bar and A in the pull-down network, plus 4, their capacitance is seen in the pull-up network, divided by 3, which is 8 plus 4, which is 12 over 3, which is 4. So obviously, when we look at simple effort, group effort, and total effort, we know that simple effort is going to be the smallest quantity. Total effort is going to be the largest quantity. Neither of them represent something very meaningful in gates such as this. Group effort or bunch effort is something in the middle, and it's going to represent something meaningful because it represents some meaningful capacitance being switched.